Assalamu alaikum and welcome back to my YouTube channel. We know how standard stochastic gradient descent works, but it can be slow and shaky, especially in complex loss landscapes. So, what's the solution? The solution is momentum. In this video, we will apply stochastic gradient descent with momentum to a small dataset and solve it step by step. You will see how the velocity changes after each sample and how the new weights are computed from those velocities. Here's a comparison of stochastic gradient descent with and without momentum. The common term in both is how the weights are updated. New weights is equals to old weight minus learning rate times the derivative of the loss function with respect to weights. But here's a difference. In stochastic gradient descent with momentum, instead of the derivative of loss function with respect to weights, we have a velocity. This velocity is exponentially weighted moving average, computed through first two equations. Beta times old velocity plus 1 minus beta times the gradients of the loss function with respect to weights. Here beta is hyperparameter. If beta is 9, 90% weightage will be given to the old velocities and 10% to the new gradients. Here we have a small dataset with 4 samples. Our hypothesis function is simple linear regression. H of x equals to theta 0 plus theta 1 x. We have some initial values. Initial weights theta 0 and theta 1 are 1. Learning rate is 0.1. Momentum value, that is beta, is 0.9. And initial velocities v0 and v1 are taken as 0. As we are using stochastic gradient descent, we will start with the first sample. We will first compute the h of x, that is our hypothesis function. After putting the values of theta and x in the equation, we get 3. Now we compute the error, h of x minus y, which is 3 minus 5 is equals to negative 2. The next step is to compute the gradient of the loss function with respect to weights. We call it L1. The equation is error multiplied by xj, where j is the input corresponding to the weights. Since theta 0 is constant or intercept, its value is 1, and theta 1 is slope and corresponds to x1, and x1 equals to 2. So gradients with respect to theta 0 is minus 2, and with respect to theta 1 is minus 4. Here we have the equations for calculating the velocities and updating the weights. We will update the equations and replace w and b with theta 0 and theta 1. So first we'll compute the velocities and then we will update the weights. Look at the first equation. The beta is 0.9 and initial velocity was 0. 1 minus beta is 0.1 and the derivative of loss function with respect to theta 1 is negative 4. So the velocity for theta 1 becomes negative 0.4. Similarly, for theta 0, beta is 0.9, initial velocity is 0, 1 minus beta is 0.1, and the derivative of loss function with respect to theta 0 is negative 2. So it becomes negative 0.2. Now we have to update the weights. Old theta was 1, minus learning rate was 0.1, and the velocity for theta 1 is 0.4. Similarly for theta 0, and we get new weight 1.04 theta 1 and 1.02 theta 0. Since the weights have been updated after the first iteration, for the second sample to compute h of x, we will use the upgrade weights. So we will put the new values of theta 0 and theta 1 in the equation and compute the h of x. It comes out to be 5.18. Then we calculate the error. Now similarly, as we did in the first iteration, we will compute the gradient of the loss function with respect to the weights, and we call it L2. After computing the gradients of the loss function, we will compute the new velocities. So in this equation, beta is 0.9 and the previous velocity that we computed in the last step was negative 0.4. So we'll put it here, and the derivative of loss function with respect to theta 1 is negative 19.28. So now we calculated the updated velocity. We will do the same for theta 0 as well. And now we compute the new weights. Theta 1 becomes 1.268 and theta 0 becomes 1.086. Based on the new weights, now we calculate h of x. After calculating h of x, we will compute the error, which comes out to be negative 6.3. Similarly, we repeat the process and compute the gradient of the loss function with respect to theta 0 and theta 1. We call it L3. Then we compute the new velocities. Old velocity for theta 1 was negative 2.28 and for theta 0 was negative 0.662. Based on these values, we will compute the new velocities and then compute the new weights. Now theta 1 becomes 1.85 and theta 0 becomes 1.209. Using the updated weights, we again calculate the h of x and then find the error. Now we compute the gradient of L4 corresponding to the last sample. Let's again compute the new velocities for theta 0 and theta 1 and then update the weights theta 1 and theta 0. Theta 1 becomes 2.696 and theta 0 becomes 1.358. Now we are done with all 4 iterations of stochastic gradient descent with momentum. Here is a summary. We have 4 samples, initial weights were 1 and initial velocities were 0. Here is how after each sample, the weights theta 0 and theta 1 and velocities w0 and w1 changes. We can see that the velocities are accumulating and increasing in the following steps. This process of accumulating speed is why momentum is so crucial for fast training. It allows the model to ignore those noisy individual sample gradients and accelerate smoothly down to the long, shallow values of the loss function. If you found this video helpful, please like, share, and subscribe for more videos on machine learning and deep learning.